Thank you for coming back, and today we are going to study the homogeneous linear system, ODE. As a long name, I'm going to write it as HLS and ODE. In short, we're going to revisit the eigenvalue and the eigenvectors. So as we discussed in the classification of mathematics models, there's two types of observation scope. One, we call it microscope observation. Another one, you remember, is called the macro, M-A-C-A-O, scopic observation. And at this microscope observation, and our mathematics model typically will be represented as an initial value problem, IVP in short, and the ordinary differential equation. In this ODE, you only got one independent variable, typically the time t. So we have already used Stellar to model and simulate a few of those examples. But ideally, I would like you to know how you can solve either by hand or by software analytically. In next hour, I'm going to show you some Maple or MATLAB code to solve it, not numerically, but analytically. I mean, you get the symbolic solution instead of numerical solution. Symbolic means your solution have this function et, cosine t, sine t, instead of all numbers. So the advantage of this symbolic solution is you can substitute it back to the equation to verify if you get the right answer or the wrong answer. You cannot do so by numerical solution. So today, as the outline, first I want to introduce quite a few concepts related with the homogeneous linear system. And then we're going to change the question to solve ODE into solve algebraic equations by the two concepts you learned before, the eigenvalue and the eigenvector. And then we're going to show you when you get the imaginary eigenvalue and the eigenvector, do not be panic. You always you can change back into real solutions, but with the trigonometry functions. And finally, I want you to solve one or two completely initial value problem. Let's start from the example we talked 2 hours ago, 2 lessons before. In the last lesson of the unit 1, you still remember we have a pure water here flow in with the 6 liters per minute, and the volume here is 24 liters, and the 24 here. From this, the speed is 8 liters per minute, and then flow back 2 per minute. And the exit speed is exactly the same. But this setting, you remember, the volume does not change. Well, we used the Stellar simulated to the solution, and all you have seen is a curve like, let me see, A goes from this, and the B goes from this curve. But that don't give you any insight except the number you want. For example, here's the time t, this is the salt amount, and you can get the solution. For example, here they got exactly the same concentration, but it's hard to verify it's right or wrong. We just know 2 points. The beginning point, t equals 0. In the end, they all goes to pure water. That is just a checkpoint. But that's not enough in some case. And we also remember we can build the mathematics equation like this in that hour. And the conceptual model, here's the change equals flow in minus flow out. That's how we got these 2 equations. And include the 2 initial conditions. At the beginning, you have 2 pounds of salt here and 6 pounds of salt here. So we got this system. What I like to do as the first step, I like to write into a matrix form. You remember I told you everything in this course is going to be end up with a matrix. So I call this as x, y. Put this prime means you take a derivative t to x, take a derivative t to y. On the right hand, if you know how to multiply, you can rewrite this into the matrix coefficient. And all you need is to check. So that system, in short, you can write as a vector equals A times itself, and the A is this matrix. Then you need to add the 2 initial conditions. You can write as x, y at 0 equals 2 and 6. So step 1, rewrite the equation into matrix form. In computation, we really only deal with this. If you use MATLAB or Maple, that's all you need. So we look at the 2x2 system. When I say homogeneous, let me point it out. There's no more other terms. If you had the other term here, then it's not a homogeneous. Homogeneous means they are all first degree. See, first degree, first degree, first degree. There's nothing else. That's a homogeneous. And in general, you can have up to any finite many variables. I have the n functions, x1, 2, 3, n. They're all the function of time t. Basically, you got the t, which is one-dimensional, and the map to r to the n-dimensional. Give an example. For the AUV, autonomous underwater vehicle, we have the n equal 9, yn unit equal 9. We get the x1, x2, x3 as the position, x4, 5, 6 as the velocity, 7, 8, 9 as all the angles. Then you got the 9 of those functions. Or each function were correlated. In reality, you might have a lot of zeros. For example, your position only related to the velocity. So in here, you got all those, we call this as a coefficients. They could be function of t, but in our application, we're going to only have constants. So if it's this complicated, no big deal. You do the same way. You write the equation as x as a vector, take the derivative, equal to a times x itself. Now, what's x? The x is going to be this x1, x2, x3, all the way to xn. That's the x. And what is the a? A, you need to get all this coefficient except x. Means a11, you can put a t here. Well, a12, a1n. As I said, we're only going to solve this with all constants. If there's no constant, some function t, you can solve numerically, but hard to solve analytically. Give you an example. If you are navigating with a rotation, if you set the path of the rotation as the function of time, and you bet those are the cosine and the sine functions here. So you are going to have a function of time. But we don't consider those hard ones. So you are right, and the equation is x prime, take the derivative, equals a, which is this, times x1, x2, x3, xn. Can you see it? That's another way to write all the n equations.